morning. Let me start off by briefly recapitulating what we had done in the last class. We had introduced the concept of a metric whose purpose is to tell us how to calculate the distance between 2 points. So, in a space, if I have 2 points, one being labeled by coordinates, let us say we are in 3-dimensional space, one being labeled by 3 coordinates x, y and z, and the other which in general we refer to in the index notation using xi, and the other point is xi plus dxi, it has slightly different coordinates. So, there are 2 points, one with coordinates xi, x, y, z are a specific example of a choice of coordinates, it could be in general, and I have another point at xi plus dxi, slightly different coordinates, and the question we are interested in is what is the length of the separation between these 2 points. And the metric tells us how to calculate this in some general curved coordinate system, curved space. It tells us that the length squared is gij dxi dxj. That is the definition of the metric, I am repeating it. Now, it is a property which I had not told you in the last class, that in a Riemannian space, so if I am working with a Riemannian space, so where Riemannian geometry holds, the metric contains the complete information about the space. So, in the Riemannian geometry, these are the geometries that we shall be interested in. The metric completely specifies everything about the space. So, once you know the metric, you can calculate everything about the space. Full information is there in the metric. Okay. And the metric, as I have told you, tells us how to calculate the length. Now, we had considered an example. So, let me just go back to the example for a few minutes. So, the example that we had considered, was the surface of a sphere in 2D. So, we had considered the surface of a sphere which is a 2-dimensional space. So, I can embed this in 3 dimensions. And for an unit sphere, I had told you that the length between 2 points on the surface in spherical polar coordinates was dl squared. This is called the line element. The length, the small infinitesimal length is the definition is called the line element. This was given by d square theta plus sine square theta d square phi, where theta and phi are the familiar polar coordinates. Theta is the axis with the angle with the z axis, and phi is the angle of the. So, if this is the point on the sphere, theta is this angle, you project it down, the angle here is phi onto the xy plane. Okay. Now, if I have a sphere of radius r, how does this get modified? Let me. So, this is a curved space. This we know, a surface of a sphere is curved, very familiar example of a curved space, because the surface of the earth is curved and it is approximately a sphere. So, if a sphere has radius r, so for a sphere of radius r, the line element dl square is r square d square theta. Now, displacement d theta corresponds to a bigger length, plus sine square theta d square phi. So, this sphere has radius r. Now, we know from our familiar experience that the larger the radius of the sphere, the less is the curvature. In the limit, when the sphere becomes infinitely large, you will not see it to be curved, you will, over any region it will appear to be flat. So, the more the smaller the radius, the more curved it is, and larger the radius, the less curved it is. So, the curvature for such a surface is quantified by 1 by the radius, and in the limit of the radius going to infinity, we have a flat space. Okay. So, this gives you an idea of what we mean by the curvature. This is a surface of constant curvature, the curvature is the same everywhere. This is a point I had not discussed in the last class. The surface of this sphere is a surface of constant, is a space of constant curvature, it has a value 1 by r everywhere. The radius, where the radius is r. So, recollect, just remember this, keep this in mind. Okay. Now, having told you this in the last class, the next point that was very important is that we have, it is convenient to think of space and time as a combined geometrical thing, a 4-dimensional space. So, we have a 4D space which is space time, and points here are events, and all events are points, different points in space time. Each event has a different position and time. So, points in this space time are events, things which occur at a different position at a different time. Now, we had introduced a line element on this 4-dimensional space time ds square, which was c square dt square minus which was the line element in the absence of gravity. In a flat space time, we have this line element. In a flat space time, this is the line element. The last 3 terms tell you the distance between the spatial distance, this tells you the time separation. And this was, we found the utility of this was that this is an invariant. I told you, I did not prove it, but I told you with sufficient indication that this is an invariant. It does not change when I go from one inertial frame observer to another. And it allows us to determine, to look at the causal relation between events. Events were classified as the null, time-like or space-like. Space-like events are not causally connected, time-like events are causally connected, null events are connected just by light trajectory. Okay. And I also told you that in Einstein's theory of general relativity, the gravitational effects gravity manifests itself as curvature of space time. So, space time is curved in a gravitational field. It is no longer, the metric is no longer this simple form, it is more complicated. I had given you one example of a weak gravitational field. A particle in a weak gravitational field would be moving in such a metric, would be experiencing such a metric. Okay. So, gravity manifests itself as the curvature of space time, where the line element, the interval has a more general form, which we can write like this. So, where the index mu takes values 0, 1, 2, 3. So, in the presence of gravity, the space time is curved and all the information about the curvature of space time is there in the metric. Okay, that is why the metric is so important. It is a Riemannian space time, it is a Riemannian, it has the Riemannian geometry, and in such a situation all the information about the curvature is there in the metric. So, that once you know the metric, you know everything about the space time, everything can be calculated. Okay. Now, the question arises, what is the cosmological metric, right? What is the now a point which I probably should mention is that the in Einstein's theory of general relativity, in Newtonian theory we know that it is the mass which causes gravity. In Einstein's theory of relativity, both mass and energy density produce gravity. So, the curvature in this metric is related to the mass distribution and the energy distribution. Okay, the stresses, how the stresses are distributed, like pressure and such things. Okay, so the mass distribution and the pressure stress distribution of stresses like pressure, they decide the curvature, which in turn is the information is there in the metric. Okay. Now, let us ask the question, what is the cosmological metric? So, what the cosmological metric tells us how to calculate distances in the cosmological space time. The question is, what should be the properties of the cosmological metric? In the last class, let me just to drive this point, the importance of this point home, in the last class I had introduced, I had briefly told you that in the presence of a weak gravitational field, the metric, the line element is of this form, where phi is the familiar gravitational potential. So, you can appreciate that this is not a flat space time. In a flat space time, this coefficient would be 1, this coefficient would be 1. Here there are differences. So, this is a curved space time, and the curvature is essentially caused by the gravitational potential. So, in this theory, the gravitational potential is the curvature of is related to the curvature of space time. Now, can this possibly be a cosmological metric for some arbitrary phi? Now, we have remember that we have made certain assumption about the nature of space in cosmology. What were these assumptions? There is a cosmological principle, what does it tell us? What is the assumption? Universe is homogeneous and isotropic. So, whatever be the cosmological metric, it should be consistent with the axiom, with the cosmological principle, universe is homogeneous and isotropic. This is called the cosmological principle. Now, if you take this arbitrary metric, this metric of a gravitational field of, let us say, this body, the gravitational field is strong near the body, relatively stronger, and then it falls off as you go far away. Is this metric homogeneous and isotropic? It is. It could be isotropic if this is spherical, but if this is not spherical, then neither, right. So, I have given you one example of a metric that is not homogeneous and isotropic. Okay. So, if you want to write down a cosmological metric, that is, we shall be guided by this cosmological principle that the universe is homogeneous and isotropic. So, one has to first determine what is the most general homogeneous and isotropic metric, where all points in space are identical, all directions in space are identical. This metric is called, so let me write down. So, this, okay, let me just tell you that this is the cosmological principle. We have discussed this earlier. And in the context of general relativity, it can be made much more rigorous. This idea of homogeneity and isotropy can be made much more rigorous in the context of the geometry of space. And people have worked out this, what is the most general cosmological metric, most general metric, that is where the space is homogeneous and isotropic. All observers in space see exactly the same thing in all directions, and this metric has a name. It was independently worked out by 3 people. So, it goes by the name of these 3 people: F. Friedman, FRW. It is usually referred to as the F. Friedman Robertson Walker FRW metric, or some people call it the Robertson Walker metric. Friedman was a Russian. And this, let me write down the form of the metric first. So, this metric can be written, the line element, the interval in this Friedman Robertson in a space time which is homogeneous and isotropic, the metric can be written, the line element or the interval rather, can be written as ds square is equal to c square dt square minus a square L square d square r 1 minus k r square plus r square d square theta plus sin square theta d square phi. So, this is the line element in this FRW, for this corresponding to this FRW metric. It is the line element in a homogeneous and isotropic space, in a cosmological space time where space is homogeneous and isotropic. Time is not homogeneous. Different instants in time are different. Okay. Now, let me explain to you. I am not going to go through the derivation of this, and I will just give you some kind of an explanation so that you can get some feeling for what this is, and we shall use this for calculations in this course, which should give us an idea of what we mean by this. Okay. So, first of all, what do we use the metric for? We use it to calculate the interval. In space time, we use it to calculate the interval between 2 events. Okay. Recollect that if you have in the usual flat space time, in the usual space time without gravity, this is what it would correspond to. Here there are some differences. Okay. Let us go through these differences and understand what is the significance of this. Now, the first point that I should tell you is that these coordinates r theta phi are co-moving coordinates. So, I had told you that we have a picture where the universe is expanding, galaxies are all moving apart from one another. So, you can think of these coordinates as being fixed to those galaxies. Those galaxies are the fundamental observers sitting at fixed coordinate points. So, these coordinates are co-moving coordinates. Okay. A of t is the familiar scale factor that we have discussed at great length already. and if the universe is expanding, then A of t is an increasing function of time. Okay. K is a dimensionless number which can have values -1, 0 or 1. Okay. And this decides the curvature, whether the space is curved or not. And the only other thing that has to be defined is L. Now, something I should tell you that all these three things are dimensionless. The scale factor is already dimensionless, I have told you, we have already discussed this. It has value 1 at present, we have chosen it like that. K can have this constant k over here can have values minus, plus 1 or 0. It decides whether the space is curved or not. Space time is curved, okay. This decides if the spatial part is curved or not. I shall discuss these things in more detail. R, theta and phi have been chosen so that they are dimensionless, okay. So, this has to have dimensions of length. If R, theta and phi are all dimensionless, question arises, how do you give a dimension of length to this, which is why we have introduced this L square. So, the dimension of length over here, this has dimension length, that is obvious, C dt. So, L is some number of dimension length which sets the length scale in this whole thing. So, L has dimension length, it is a length scale, okay. Now, in many places you will find that this L has been absorbed into the scale factor, and the scale factor has dimensions of length. In many textbooks you will find it, okay. I am just writing it separately because we have started out with making a scale making a dimensionless, right. Since we have started out making a dimensionless, I thought let us not change our notation and we can just accommodate the dimension of length by introducing an extra length scale L over here. Okay. So, there is a length scale L over here. Now, let us try to understand what this means. Okay. What is the implication of this? We will not go into the details of general theory of relativity now of calculating the curvature, etc. Let us just go ahead and try to get some kind of a heuristic, that is intuitive feeling for this thing. So, let us first look at what happens when the constant k is equal to 0. Let us just consider this case first. Here this interval becomes ds square is equal to that is what we have for the interval. Now, this is already familiar. It is the Euclidean metric in flat space time, Euclidean metric in flat space time space. This is the Euclidean metric in the usual 3-dimensional flat space written in spherical polar coordinates. I hope that is obvious. In a usual 3-dimensional Euclidean flat space, this is the line element. It tells us the distance between 2 points at a separation r dr d theta d phi. Okay. So, this is very familiar 3-dimensional Euclidean space, flat Euclidean space. So, the flat space corresponds to this k. The spatial curvature is determined by the value of k equal to 0 is the flat space. Okay, this is the usual familiar flat space. Now, in this case we can absorb this L into this expression by giving the dimension of length to R. So, if I redefine R to be L into R, so I am redefining R to be L into R, okay. Then I can just absorb it everywhere because there is a factor of R square in both these terms, all three terms actually. So, I can just absorb this L square inside this by redefining R to be in units of length, okay. So, this L actually does not have any very significant role, does not play a very important role in this particular case where K, the curvature which is 0, K is 0, the space is flat. And in Cartesian coordinates, this was in spherical polar coordinates, in Cartesian coordinates I can write ds square is equal to c square dt square minus a square d square x plus d square y plus d square dx d square z, right, dx square plus dy square plus dz square, sum of these three. I have absorbed this length L inside this x, y and z inside R, and then I can write it like this. Okay. So, the spatial part here is flat, it is a flat space, the spatial section is flat, it is infinite flat space. Now, let us just see, let us consider two observers at fixed value of x. At a given time t, how much is the time interval taken for a light signal to propagate very close between these two observers? We assume that this a of t does not change in the time interval that light propagates between these two. So, delta t, the time light takes, or c delta t is a t into delta x, right. So, this is the proper distance, the actual this is what we mean by distance, right. How do we determine the distance between 2 points? Send a light signal, how long does it take to go from one point to the other? That will tell us, divide by the speed of light, it will tell us the distance, right. So, this is the distance between these 2 points, it is what is called the proper distance. Okay. Now, for these two galaxies or observers at fixed values of x, at a later time if the scale factor has increased, what is going to happen to the proper distance? It will increase, right. So, if a of t is an increasing function of time, at a later time the proper distance between these two observers is going to increase. So, it is going to become larger at a later time if the scale factor is an increasing function of time. Okay. So, this delta x, as you can realize, is the co-moving distance between these 2 points. So, as the universe expands, the scale factor increases and the proper distance between these 2 points increases, the co-moving distance remains fixed. Okay. So, this gives us a picture of of this space time. It is just the usual flat space time that we are familiar with, except for the fact that it is expanding. There is a factor function a of t over here. If this a of t were 1, this would be the usual flat Minkowski space time with no, just the normal space time that we have. Okay. So, there is just this extra function of time, the scale factor over here, that is the main thing, main difference. Okay. This space time is curved. If you calculate the curvature of this space time, it is curved, but the spatial part is flat. Okay. The spatial sections are flat, the space itself is just flat, whole of space time, it is actually curved because there is a function of time coming in over here. Okay, so if we calculate the curvature of space time, 4 dimensional space time, it is curved. Okay, so I have given you some idea of this k equal to 0 situation. Now let us consider k equal to plus 1. Here the line, the interval ds square is c square dt square minus a square l square, then I have d square r 1 minus k r square plus r square d square theta plus sin square theta d square phi. OK is already taken to be plus 1, so we do not have to write this again. Okay, there is no need to write it explicitly again. K is plus 1, right. Now you will realize straight away that r is restricted in value. R is a dimensionless number here, it is restricted in value to what range? If r is if r is infinity, what happens to the denominator? So what is the range over which r is restricted? R is restricted in the range greater than 0, greater than equal to 0 or less than equal to 1. What about minus 1? Can r have values minus 1? Is r in the range minus 1 to plus 1 or 0 to 1? So let us, okay, so we shall come back to this. So before we come to this point, let us to get an understanding of what this is, what space this is, what kind of a space this is. See, this is not the flat space, that is obvious, because there is this extra factor of 1 minus r square. Also the range of r is restricted. If this 1 minus r square were not there, it would be the usual flat space. Okay. Now to understand, to get a feeling for this, let us start studying a circle. Let us first look at a circle. Okay. So a circle, let us just look at this. A one dimensional space S1, it is called S1, it is a one dimensional space, it is a circle. Okay. There is only one coordinate that you require to describe it, and we can call that phi. So phi has the range 0 2 pi. Okay. And the line element on this circle dl square is r square, the radius of the circle, into d square theta. Okay. Now let us go to 2D. This is 1D. So now this, from this circle we go to a sphere. Now you can think of this sphere as a collection of circles. Okay. So on each circle there is a length d phi. Now, what is the radius? If the radius of the sphere is r, this is, so the phi is this angle over here, which is what you get if you project it down and measure it. Now, question is, what is the radius of this circle? R sin theta, where theta is this angle. So, the radius of this circle is r. So, the length line element becomes r square d square phi sin square theta, that is the radius. So, that is the length along this circle. Now, I have on the surface of this sphere I have another possibility. So, I can think of this sphere as a collection of circles, right. So, I can think of this as a collection of circles, and the angle theta, what is the range of this angle theta? What happens to the radius of these circles? It starts from 0, then it goes to the maximum value, and then it again shrinks to 0 over here, right. So, I can think of a sphere as a collection of circles whose radius starts from 0. So, there is another variable theta which decides the radius of the circle. This goes from 0 to pi. Right, theta goes from 0 to pi, and the line element here is d square r square d square theta plus, so that is the line element, that is the length in this direction, and this is the length along these circles which are already there, whose radius is changing as I go from here to here. So, I can think of this as a collection of circles which have this problem, which I have put together into a 2-dimensional space. Okay. Now, let us come back here, and it is obvious that now this should be, r can take all values between -1 to 1, right. This is allowed, that is the range, allowed range of r, -1 to 1. Okay. Right. Now, we want to interpret this spatial, only the spatial part. Okay. So, let us come back to this, only the spatial part. We would like to interpret a 3-dimensional space whose line element dl square is d square r one minus k r square plus r square d square theta plus sin square theta d square phi. Okay, we want to interpret this 3-dimensional space which has a line element like this. Now, it is convenient to think of this as to introduce a new variable. So, let us do that. Let us introduce a new variable, k is 1. Let us introduce a new variable, okay, and r is sin chi. Okay. R is sin chi. So, in terms of this, this can be written, this whole thing can be written as d square L dl square rather is equal to, what does this become? dr is cos chi d chi. So, this is also cos chi. So, it cancels out, this becomes d square chi plus chi square plus sin square chi into t square theta plus sin square theta d square phi. Okay. Let us now interpret this. All I have done is I have done a change in coordinates. Now, we would like to interpret this. Question is, how will we interpret this? Okay. Now, to interpret this, just go back to this. On the surface of a two dimensional sphere, you can write the line element as d square theta plus sin square theta d square phi. Okay. Just see. So, this is a collection of circles whose radius changes as sin square theta, sin theta, right. This is a collection of circles whose radius with varying theta. So, at each theta there is a circle. Okay. At each value, if I plot it in a different way, theta, for each value of theta there is a circle, and the radius of that circle is changing as sin theta. Okay, I have put together all of these circles to form a two dimensional space now. Okay, one is theta, the other angle is phi. If you want to interpret this, how will you do it? Now, you see this, each of this is a sphere, two dimensional sphere. Each of this is a two dimensional sphere. Now, I have introduced a third variable chi. So, for each value of chi, there is a sphere. Just like there was a circle for each value of theta, for here for each value of chi there is a sphere. I cannot really draw it because I have to embed it in 4 dimensions if I want to draw this, right. The sphere I embedded in 3 dimensions, then the surface I got was 2 dimensional. Here I have to embed this in 4 dimension, then I will get a 3 dimensional surface. Okay. But the point I am trying to make is that for each value of chi you have a sphere whose radius is sin square chi, and the sphere itself is 2 dimensional. I have introduced one more dimension chi. So, I have a 3 dimensional space. This is a 3 dimensional generalization of a sphere. It is a 3 sphere, right. You can see that it is a 3 dimensional generalization of a sphere. This is a 2 sphere, 2 dimensional sphere. This is a 3 sphere. Okay, this is a 3 dimensional generalization of a sphere. Okay. And the range of chi again is from 0 to pi by 2. 0 to pi. So, what we had written earlier was correct. R being -1 is obviously, yeah, let me rectify it here. No, right. R is the distance from the origin. So, R has to be 0 to 1, not -1 to 1. Okay. So, this space can also be written like this in terms of another variable chi. This is like a generalized spherical polar coordinate system, okay, like this. So, just try to visualize it in 3 dimensions. This is all in, this is 3 dimensional. In on 2 dimensions, it is easy to visualize. If you are on the surface of a sphere, that surface of a sphere starts with a point where you are. I am here, so this is a point. Now, that is the surface of the sphere, right. I am drawing circles on that. The picture is not clear. This is the surface of a sphere. I am here, then I can draw a circle here, a circle here. What is the largest circle I can draw on the surface of the sphere? It has, what is the radius of the largest circle I can draw on the surface of a sphere? Is the radius of the sphere. Then if I, so I am starting from, let us say, the north pole, that is the point. Just think of the latitudes. At the north pole, at a point, then there is one latitude is a circle, a next latitude is another circle. As I keep on going down, what is going to happen? The circle is going to increase and increase, and the equator is going to be maximum. Then as I go into the southern hemisphere, what is going to happen? It will again decrease and finally become 0 again, right. So, this is exactly the same thing. We start at chi equal to 0, it is a sphere now, not a circle, of radius 0. Then you increase chi slowly, you reach the equator at pi by 2, where it is a sphere of maximum radius. Again at the other pole, when this is pi, it again becomes 0. Okay. So, this is a 3 dimensional space, which is a generalization of the 2 dimensional sphere. Okay. And one can calculate the volume, it has a finite volume, just like a sphere has finite volume 4/3 pi r cube. This also has a finite volume, finite region of space. There is a finite distance which you can propagate in this. Okay. So, it is a 3 dimensional generalization of a sphere. If you go in this direction here on this, in this space, if I travel in one dimension, in this space if I travel in one direction, I cannot go to infinity, I will come back from the other side. Just like on the surface of a sphere, if I travel like this, I will go around and come back. In this space, if I travel like this, I will come back to the same point. Okay. So, we have discussed, to some extent we have now we can calculate various things in this space, and I have told you how to get some idea of what this represents. Now, what is this value L? Okay. So, now we have these spheres and we have again the same thing, co-moving observers sitting on these spheres, and the distance between them is increasing with time. The only question that remains is how to get the value of L. Okay. Without proof, I will tell you that the value of L is C by H naught into 1 by square root of omega curvature naught. The modulus of omega curvature naught. And k positive, k equal to 1, corresponds to omega curvature less than 0, negative. So, these are cases where that constant of integration which we had in the dynamical equation has a negative value. So, if I have a model with just matter and the constant of integration which is there in this omega curvature has a negative value, what is going to happen to the expansion? Recollect, how did we interpret the constant of integration? As the energy. So, if the energy is negative, what is going to happen? Is the universe going to expand forever or is it going to collapse? Collapse. So, these are models which will collapse again in the presence of just matter. In the presence of just matter, these models will collapse again. Cosmological constant can make a difference, but in the presence of just matter, this model is going to collapse again. Okay, so, L is determined by the value of omega curvature naught. The larger the value of omega curvature naught, the smaller the value of L. Okay. The next point is that the radius, so this is a 3-dimensional sphere. What is the radius of this 3-dimensional sphere? The radius, so what plays the role of r over here? So, the radius of this 3-dimensional sphere is a, so radius a t into this L. Okay. This is the radius of this 3-dimensional sphere. So, curvature of the sphere, okay, not of the space time, of the sphere is equal to 1 by a into L. So, here the spatial sections are 3-dimensional spheres, which is quite consistent with our understanding, because the surface of a sphere we know is homogeneous and isotropic in 2 dimensions. Each point on the surface of a sphere is exactly same as any other point, right. There is no way you can distinguish between them, all directions are same. It is exactly same thing here, it is in 3 dimensions. The space could also be a 3-dimensional sphere, every point is identical to any other point, has same properties, all directions are identical, and we have the radius of that 3-dimensional sphere is this factor over here, which is a into this number L. This number L, without proof I am telling you, is c by h naught into 1 by square root of omega curvature, the modulus of that. And if k is equal to 1 positive, this omega curvature has a negative value. Okay. This you get when you take into account the Einstein's equation. Okay, I shall come back to this issue later again. Right now, just take it. That okay. So, this is a space of, the space over here is a space of constant positive curvature, constant in space, it is constant everywhere, same value everywhere in space, it changes with time. Okay. Positive curvature, because it is a sphere. K is equal to -1, let me just briefly mention it, K equal to -1, it is a negative curvature space. The space, the spatial sections are of negative curvature. Okay, it has negative curvature. All that you have to do is you have to replace sin chi by sin hyperbolic chi. Okay, and you can, everything else is the same, because this becomes plus, okay, and that is a space, you can write it again in that polar kind of system, or it is equally good to write it in this way. Here again the space is curved, it has got negative curvature, the length scale L is equal to again the same thing, c by h naught 1 by root of omega curvature naught. Here omega curvature naught is positive, okay, in this case, and k equal to 0 omega curvature is 0. Okay, in k equal to 0 omega curvature is 0. Now, another point that I should tell you, that the interpretation of this number c by h naught, which occurs in this length scale L, 1 by h naught I have told you is the present age of the universe, an estimate. So, what is c by h naught? It is, yeah, it will give you an idea of a particle. Suppose a particle starts moving at the time of the Big Bang. So, there is a particle that starts moving at the time of the Big Bang. then in the present age of the universe, what distance will it travel? Of the order of c by h naught. This is the furthest distance a signal could have propagated in the universe. That is the furthest distance you can see. This sets the length scale of the furthest distance that you can see essentially. Okay. It is called the Hubble radius. Estimate its value. Okay, how much is it? So, this length scale L that appears over there is important only when you have curvature, and it has a value which is the Hubble radius into 1 by square root of omega curvature, modulus of that. Okay. So, in today's lecture I have introduced the cosmological metric. The coordinates that we are using, the spatial coordinates, are co-moving coordinates. Okay. There is a length scale L that we have introduced, which is the curvature length scale, and there is a scale factor which we are already familiar with. Now, the spatial part could be either flat or it could be curved. The curved ones are spaces of constant positive curvature or constant negative curvature. What do we mean by constant? It is same everywhere. Okay, a space could be curved in a way that depends on position, varies with position, but cosmology requires that the curvature be same everywhere. Okay, so you could have a space of constant positive curvature or constant negative curvature. These are the three possibilities. Okay, and in the next class we shall discuss how we can use the metric to calculate various things. The metric essentially becomes very important if you want to see the propagation of light in the universe, because the propagation of light you cannot study without relativity. Slowly moving objects you can deal without relativity. Okay. And everything that we see is through light. That is why the study of propagation of light is all that important, and this is an issue we shall take up in the next class.